So in my previous class we have already discussed about the ionization potential as well as excitation potential of the electron in an atom. Today we will discuss some problems from the chapter atom. We have already discussed how to calculate the energy and radius of hydrogen atom, and you know the expression for wavelength of hydrogen atom, that is 1 by lambda equal to RH whole into 1 by n1 square minus 1 by n2 square. Here lambda is the wavelength but 1 by lambda is the wave number. Suppose one problem is here that find minimum and maximum wavelengths of Balmer series. For Balmer series, the Rydberg constant is fixed, that is RH equal to 1.097 into 10 to the power minus 7 meter inverse. And for the minimum and the maximum, you have to remember one thing, that when wave number means 1 by lambda reciprocal, so lambda is the wavelength. When lambda is maximum, then 1 by lambda is minimum. So when we have to calculate the maximum wavelength means 1 by lambda must be minimum. For minimum value of 1 by lambda, the electron must jumps just from the higher orbit to the lower orbit. For Balmer series, n equal to 2, n1 equal to 2. So for maximum wavelength, that electron must come from just upper orbit, that is n2 equal to 3. When the electron jumps from just third orbit to the second orbit, then the wavelength must be maximum. So you have to put only in case of n2 you have to put 3. So RH equal to 1 by 4 minus 1 by 9, 1.097 into 10 to the power 7 into 5 by 36. So this is the value of lambda maximum. You have to calculate. We will get in terms of angstrom 6563 angstrom. But for minimum wavelength, you have to remember that minimum wavelength means lambda is minimum. So 1 by lambda must be maximum. So for the minimum wavelength, electron must jump from very far distance. So n2 equal to infinite. So 1 by lambda minimum equal to RH 1 by 4 minus 1 by infinite. This 1 by infinite is 0. So lambda minimum will become 4 by 1.097 into 10 to the power minus 7 meter. We have to express in terms of angstrom, that is 3646 angstrom. So for higher wavelength or maximum wavelength, it is 6563 angstrom, and for minimum wavelength this is 3646 angstrom. Here we have calculated the maximum and minimum wavelength of Balmer series. Like that, other 4 types of the series are there, just like Lyman series, Paschen series, Brackett series, Pfeffer series. You can calculate the minimum and maximum wavelength for all the other series also by putting this formula. And next problem, find the kinetic energy of a photon associated with radiation wavelength 900 angstrom, H equal to 6.6 into 10 to the power minus 34 joule second, that is the Planck's constant, and C equal to 3 into 10 to the power 8 meter second inverse. We know that kinetic energy E equal to h nu. Nu is the frequency, and in terms of wavelength that is h nu is c by lambda. So kinetic energy will become, putting the value for Planck's constant c and lambda, we can get 2.2 into 10 to the power minus 16 joule. Next, another problem is here. The second member of Lyman series in hydrogen atom has wavelength 5400 angstrom. What is the wavelength of first member? So here one type of different type of question is given, that second member of the Lyman series in hydrogen atom has wavelength this much. What is the wavelength of the first member? But for Lyman series we know the formula, that 1 by lambda equal to r whole into 1 by 1 square minus 1 by n square. This formula we know, that 1 by lambda equal to r 1 by 1 square minus 1 by n square, because for Lyman series all the radiations, all the electrons will jump from higher orbit to the first orbit. So in case of n1 we have to put 1 here, and for the first member n equal to 2, so 1 by lambda 1 r whole into 1 minus 1 by 2 square, that is r into 3 by 4. And for the second member n equal to 3, so 1 by lambda 2 equal to r whole into 1 minus 1 by 3 square. Here we have to put 1 because for Lyman series this n1 value is 1, so it will become r into 8 by 9 by calculating, and just dividing 1 by 2 we can get lambda 1 by lambda 2 equal to r into 8 by 9 into 4 by 3r equal to 32 by 27. So here lambda 1 becomes 32 by 27 into lambda 2, and given the lambda 2 is given because the Lyman series, the second member has the wavelength 5400 angstrom, and putting instead of lambda 2 5400 angstrom we can get this mass value, that is 6400 angstrom. Next, here one problem is given regarding the formula of radius of hydrogen atom. We have already calculated, that is n square, r equal to n square h square epsilon naught divided by pi m square. This formula we have already known, but here the question is like that, if x is the radius of first orbit of the atom, what will be the radius of the second orbit of the same atom? X is given, the radius of the first orbit, and we have to calculate the radius of the second orbit in terms of x. That means how many times it will lesser or smaller, we have to calculate. We know the formula for radius of hydrogen atom, that r equal to n square h square epsilon naught divided by pi m square. You have to see that one. If you have not remembered, you have to see the expression for radius, and in the expression for the radius, except this n square, all the values are the constant, just like n square h square epsilon naught. H is the Planck's constant, epsilon naught is the permittivity, divided by pi m square, pi m e, all are constant. So we can take r proportional to n square. That means the radius of the orbit depend upon the number of the orbit as the square, or directly proportional to the square of the number of the orbit. So simply we can get r2 by r1. r2 is the radius of the second orbit, r1 is the radius of the first orbit, equal to n2 square by n1 square, or that is equal to 2 square by 1 square, that is equal to 4 by 1. Here we have given that r1 equal to x. We have to calculate this r2. So r2 equal to, putting the value of r1 x here, we can get r2 equal to 4r1, or r2 equal to 4x. In terms of means instead of r1 we have to put x. So the second orbit radius is 4 times that of the radius of the first orbit. Then next question, how much energy in joule is required to shift an electron of hydrogen atom from third orbit to the fourth orbit? This is one simple question I have already discussed. In case of that excitation potential, that an electron is in the lower orbit, it just want to move to the higher orbit, how much energy it will require. So energy E1 of the electron in the first orbit of the hydrogen atom is minus 13.6 eV, and energy E3 in the third orbit is E3 equal to U1 by 3 square, that is equal to minus 1.51 eV, and energy in the fourth orbit we already know, minus 0.85 eV. This one we have calculated in that energy level diagram. This all the energies we have calculated. So energy gained by the electron to go from the third to the fourth orbit, we have to just subtract the energy possessed in the fourth orbit and to the energy possessed in the third orbit. So minus 0.85 is minus of minus 1.51 eV, that is equal to 0.66 eV. This eV, electron volt, we can convert this electron volt into joule. It is given that 1 eV, 1 electron volt equal to 1.6 into 10 to the power minus 19 joule. So this one is 0.66 into 1.6 into 10 to the power minus 19 joule. Then here I have already discussed the another question that is same as the first, that find the longest and the shortest wavelength of Lyman series. We have already discussed for Balmer series, and here we have to discuss for the Lyman series. For Lyman series, first N1 is 1, and for minimum it will come from 2, then just the top orbit, second orbit. And so putting this value and putting the value of that reservoir constant, we can get 1215 angstrom. And shortest wavelength of the Lyman series, for the shortest wavelength we have to put N2 equal to infinite. Shortest wavelength means this 1 by lambda must be maximum. Lambda is minimum but 1 by lambda is maximum. So 1 by lambda equal to R whole into 1 by 1 square minus 1 by infinite. We can get 912 angstrom. This is a very important question, that what is the longest and the shortest wavelength of Lyman series, you have to remember. And you have to solve two questions. This is just task for you, that find the shortest and longest wavelength of Balmer series. I have already discussed this one. You have to solve again and find the shortest and longest wavelength of Paschen series. For Paschen series, for minimum value you have to put just the above orbit, and for maximum value you have to take that one, you have to calculate like that. And next question, that what is the energy required to remove an electron from second orbit of hydrogen atom? Energy of the second orbit is, we know, minus 13.6 by 2 square, that is minus 3.4 eV, but ionization energy we know 0 minus of 3.4 eV, that is equal to 3.4 eV. This much energy is required to remove the electron. This is the ionization energy, we can say, and the associated potential also we can say ionization potential.